Ideal vertical jump. There are many different ways the vertical jump can be carried out, as many people will not have access to the technology professionals can use. However, in this slide we'll go through the ideal way the vertical jump can be set up. Ideally, for the vertical jump, force plates would be used, as they take 1,000 measures per second. A force plate measures the reaction on the ground that is generated through the opposite force against it. This can be used to measure an athlete's vertical height reach when jumping, which is very important in basketball, as a high vertical will help for dunks, blocks, and layups. It is important to make sure that it is important to make sure it is calibrated before using, so that the result will be accurate. This can then be recorded to see the movement of your performer when jumping. This can then be recorded to see the movement of your performer when jumping. This can be in 2D or in 3D, which can be done through placing markers onto the performer and using a 360 camera. It is really important that this is standardized, meaning the markers are placed on the same spot of each performer, or it will be incomparable. Collecting the 3D data will allow people to analyze the jump from all angles, with lines creating the 3D jump, which allows you to see every part of the jump. A meter ruler should also be placed next to the performer before doing the jump, as it can be used as an example for measurements when analyzing with the technology. When collecting the data, it is also important that the camera settings are set correctly to record the data accurately. For example, the sampling frequency frame rate needs to be set to high, as it will give a more defined image with lots of pictures showing the full movement. A good camera can take 1,000 per second. The shutter speed should also be set correctly, so the shutter opens and shuts quickly so that light is let in effectively, as this will have a massive effect on quality to not make it blur while attaining a well lit shot. As well as the camera settings, it also needs to be positioned in the right place. For example, the image needs to account for a movement that will go on in the field of view, so that it will capture everything. It should also be perpendicular to the performer, and should be in a straight line so it is not looking down or up and is flat, meaning that there is no tilt. Video footage can then be placed into softwares like Darfish, as angles and distances can be measured and performers can be compared. Ideal 20-meter sprint. The ideal way to carry out a 20-meter sprint test would involve using speed gates. This would be set up along the 20-meter distance at intervals of 5 meters. This would allow for human error to be eliminated, as the time in which the performer passes through each interval would be accurate, whereas if it was timed on the phone, it wouldn't be as exact, as not only would it be a bit subjective, but it would also involve the reaction time of the timer, which would increase the time. It is important that these speedy gates are calibrated to 0 to begin with, so that when the performer begins, the time will be taken from 0 seconds. The setup of the camera should also be perpendicular to the runner, and ideally it would be placed on a track that would allow it to follow the runner throughout the 20 meters. If this is not possible, the camera will be set up in the middle, and triangulation will be used, so that it made a 3-4-5 triangle, as this will give the next best view for the activity. If the camera is being panned, it is important this is done without tilting becoming involved. The camera would also be evenly pitched so there is no tilt or roll to begin with. However, using this setup we may get some perspective error, which can be misleading, meaning that things may be seen as bigger or smaller because of the angle or distance away from the camera. However, if you're using the track and the moving camera, this technique will show the right angles as it will be perpendicular the whole time. However, not many people will have access to this technology. The camera would also be set up with the same settings as the vertical jump, meaning that a lot of pictures can be taken with a high frame rate and that the shutter speed is correct, so that enough light is let in, but not too much that it blurs the image. Of course, we do not have the equipment that would be used in the ideal model, like the force plates and the high level cameras, so we use different equipment to measure both the 20-meter sprint and the vertical jump. For the vertical jump, we use the jump meters. This equipment is a piece of string attached to Velcro and technology that wraps around your waist. It is important that once it's around the performer, the technology is calibrated and set to 0, so that the person's height doesn't affect the extent to which the string is increased. The performer can then jump and the string will of course extend and the height reach will be measured. The camera will once again be set perpendicular to the performer, as this will give the best and least deceiving view. We also held a meter ruler next to our performer before the jump, as this goes and analyzes a measure of what 1 meter is, so that we can use technology and it will automatically know the measurements of each thing. This jump was a standard vertical jump, so every performer took no step before making the jump. Similarly with the vertical jump, we could also not use the ideal equipment for the 20-meter sprint, as they are expensive. Instead, we measured out the 20 meters exactly as it should be, and placed cones instead of speed gates at each 5-meter interval. Due to this, we used stopwatches to measure the time it took for the runner to pass each of these intervals. We did this through placing someone with a stopwatch at each cone that they would start as the runner began and stop when the runner had passed the cone. This gave us the best measure of time we could produce, as if one person did it, prospective error could cause the timer to stop the timers when they perceived the runner to pass, which may not be correct because of the position they would have to stand in. Like said, this is because things look bigger and smaller. This error would also likely be seen with how we set up the camera, as it would not be possible to tell exactly when each person has passed the cone. Once again, we tried to set up the camera in the middle of the 20 meters in our best attempt to make the 3-4-5 triangle using triangulation, as this would give us the best view, as we did not have a camera that could move along a track. We can analyse our players' performance in the vertical jump and compare it to the other performances to identify components they need to improve to make them a better basketballer. As can be seen with the bar chart above, my performer achieved a vertical jump height of 34 centimeters. This is relatively low compared with the comparable data, as the group average was 40 and the better player reached a height of 42. The NBA Elite got 45.5, however it might be unfair to compare to this. This highlights the fact that my performer needs to improve the height they can jump, meaning the force they exert onto the ground. It is important they improve this, as jumping plays a massive role in basketball, as a high vertical makes it easier for layups and dunks to be made, as well as giving the performer a better chance to block a shot. The low score may be a result of poor technique, or jumping which could be assessed in the video. However, it is likely due to the power the performer has. Using the body mass of the player and the height they reach, this value can be estimated as shown in the second bar chart. This chart proves that the peak power produced by my performer is likely a reason for the low height reach, as it is significantly low compared to the 5,700 and 8,400 produced by the better player and the NBA Elite respectively. This suggests that in order to improve the vertical height, the player should train on improving their power, as not only should this increase their vertical jump, but may also improve their 20-meter sprint, as this involves power also. From the 20-meter test, we can use the data collected to form graphs and tables that illustrate linear aspects that would be seen in basketball. For example, the first graph shows that my performer took exactly 4 seconds. To complete the 20-meter test. This is 0.3 seconds above the group average, and is a big 0.9 seconds behind the better performer, while being 1.09 behind the NBA best, which suggests this is a big weakness for my player. This could be down to a number of factors, with the main two including acceleration and velocity. When interpreting the velocity time graph, many observations can be made, as it is very different to the better player's velocity time graph. First notable thing is the similarities between the peak velocity/speed of the two players, as both my performer and the better performer reaches a max velocity of 7.14. This suggests that speed may not be the problem, as they both reach the exact same maximum speed, meaning they are both similar in this aspect. However, it is clear to see that my performer is unable to maintain this maximum speed for any more than a second, whereas the better performer can remain at that speed for a longer period, as it does not drop from when it reaches it. This may suggest that my performer is unfit, as he is unable to maintain his maximum speed, even for only a few seconds, but also suggests that the player needs to work on keeping a high speed, as if this was in basketball scenario, despite perhaps having the speed he might not get to the ball, as he would slow down and decelerate, as seen in the acceleration graph, very shortly after reaching his max speed. Finally, it can also be seen that my performer's initial acceleration is also poor, as ideally you want to accelerate the fastest to begin with. It can be seen that he accelerates more after 1.6 seconds. Furthermore, this can be seen in the differences between the two velocity graphs, as the better player reaches their max speed in 1.6 seconds, whereas my player reaches their max in 2.3 seconds. This is something that needs to be improved, as acceleration is extremely important in basketball, as usually the sprints are very short distances, and therefore quick bursts of acceleration is needed to reach the ball before a competitor, and therefore it is important to reach the max speed as quick as possible. Evaluation. Overall, I think the numerical model is good and useful for analysing performance. However, there are also disadvantages that come with it. One advantage is that it can be extremely useful for skilled performers, as they are likely already very good at most aspects of their given sport and only need very small improvements that this model can offer. Furthermore, it is a less subjective way of looking at performance compared to some models, as this mainly involves data and numbers. This allowed for easy targets of other players' performances. The tests are also usually quite simple and easy to set up and carry out, and can be done with a range of equipment, while also being a great measure of how close you are to reaching your goals. The disadvantages of this model are, however, mainly to do with the equipment, as the perfect way to carry out this involves very expensive equipment that is unaffordable for most. This, paired with the high level understanding that is needed, makes it difficult for low teams to use this form of analysis.